In this module, we will introduce ourselves to the concept of integration, which along with the concept of differentiation or derivatives is the central concept in calculus. Here we will be looking only at integration of functions of one variables. Later on in other modules, this will be generalized to function of more than one modules. So once again, recall that what we have with us is a function f defined from a domain D to some range R. Typically, this domain and range are real values. So the concept of integration is exactly as fundamental as the concept of differentiation, and it shows up in chemistry in so many different contexts. For example, if you have a certain amount of gas in a cylinder and you're compressing or expanding this gas and you want to calculate the amount of work done by the gas or on the gas during this process, which is important because this would amount to, for example, how much air conditioning can you provide in a room or how much heating can you provide in a room. To calculate this work done, you would use an integral. Similarly, in NMR spectroscopy, the amount of energy absorbed or released by nuclei undergoing spin flips would again be measured by calculating the integral of the signal intensity multiplied by the chemical shift frequency. Through the course of whatever class you are taking, which these modules are supplementing, you will see more and more examples of integration. And in the homework problems also, I have given some more chemistry related examples, but for now we are going to look at integration from a mathematical perspective. So an integral can be thought of as an antiderivative. By that, what do we mean? What we mean is that if we had a certain derivative f prime of x, so what does a derivative look like? It's a function. So the question we are asking is, what is it that we had to differentiate in order to get this derivative? So we know here it has to be some f of x, but let's say we did not know this f of x. Let's say all we knew was f prime of x. What was the f of x that led to it? This is the question we are trying to answer through integration. That's one way of looking at it. That's not the only way of looking at it. But so what does it mean? So in other words, you could have written this equation as df of x is equal to f prime of x dx. Now, if you want to calculate f of x, here comes the definition of integral. It is given as f of x is equal to integral, and this is the integral symbol. It looks like a big S stretched in one direction. It's like a S got inside a black hole and then changed its mind and came out halfway through, something like that. So this is going to be integral of df of x, which is the same as per the above equation as f prime of x dx. So this is the key definition of integral in one variable. Let's see what it means. What it really does is to take a curve g of x. This g of x could have been f prime of x, for example, some generic g of x defined as a function of x, and integration involves measuring the area under this curve moving from a certain point A to a certain point B. So if g of x was the f prime of x that we had been given, then area under curve would be the integral that we are studying. So let's try to understand what does this mean and where does this come from. Specifically, in order to understand this, let's look at one of the most basic examples from physical chemistry, which is work done, pressure volume work done for an ideal gas, pressure volume work done for the case of an ideal gas. So for an ideal gas, we know that pressure multiplied by volume is equal to nRT. And what we would like to do is to calculate the work done by an ideal gas as it is expanded or changed from some volume VA to VB. So we know this will be given by pressure as a function of volume. So we are doing this at constant temperature as the volume changes. So this would be the integral in this case. So now we can plug in the formula for P as a function of volume. That would be nRT divided by V dV. So far, why did I introduce an integral here? Because the work done in this case, if you had a pressure volume plot and if you wanted to plot the pressure versus volume, you can see at constant T, it's going to be 1 over volume. So it's going to look something like this. So what you're doing here is at any particular value of the volume, you are calculating this area. Then you change the volume slightly and we calculate this area and you sum it up. And it is this operation that I am denoting as the symbol of an integral. So this will be nRT by V, starting from some volume VA up till some volume VB. nRT are constant in this process, so I can pull it out. It will be nRT 1 by V dV, VA to VB. So if you go back and look at this equation over here, f prime of x now corresponds to 1 by V in this case. So f prime of x has been replaced by 1 over V, and we want to figure out what is that function which we differentiate would give us f prime of x. So we want to figure out df by dx is equal to f prime of x, where we know f prime, in this case, instead of f prime of x, we have 1 over V. That's why I'm using this symbol. It's not the same. That's the analogy that we have over here. So if you have been through the derivative module, immediately hopefully you should recall that the differential of log of x is what gives us 1 over x. Therefore, d log of volume by d volume would be 1 over V. In other words, this integral is nRT, and integral of 1 over V dV can be replaced by ln of volume. And what we have here is a square bracket. And this is something we are going to talk about just in a bit as to what it means in context of so-called definite and indefinite integrals. But here we are calculating this volume as we go from VA to VB. And the way it is done, and I'll explain to you what it means, is to take the value at the top point and subtract from it the value from the bottom point. So this is the work done by the ideal gas as it is expanded from volume VA to VB. So what does this really mean? What did we do over here? So for this, let's look at our pressure volume curve once again in a bit more detail. So we had our pressure axis and our volume axis. And for the ideal gas, we had a curve that looked like this. So what we have done in this is to break it, and let's say this was our starting volume VA, and let's say this was our starting volume VB. So what we have done is to break it into chunks of delta V that start from VA and go all the way up to VB. So let's say we have broken this into chunk 1, 2, 3, 4, ... chunk n. So the work done, as you will recall from basic physics, is pressure times change in volume, right? Pressure times change in volume is the work done. This is not calculus, this is basic physics. And there must be a model somewhere that talks about it, but not in this course. This is just an example. So what would this be? This would be approximately pressure in this region. As you can see, the pressure changes from here to here, but let's say we take an average of this. We take the pressure around there. Let's call it pressure at V1 multiplied by delta V, because these changes are all equal to delta V. That amount is constant. Plus pressure at V2 multiplied by delta V, plus dot 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 pressure at Vn multiplied by delta V. So let's actually call this as small n, as capital N, this last interval. And you will see why it's useful in a moment. So let's call this as capital N. So this can be written as summation small n going from 1 to capital N, P of V small n multiplied by delta V, right? This is compact form of writing it. So as n tends to infinity, an integral is just a compact way of writing what this thing becomes. Summation n is equal to 1 to n, P of Vn delta V. It tends to, it's not exact, it tends to, because in order for this to happen, n must become exactly infinity. So that's a limit that we are approaching. This becomes integral Va to Vb, P of V dV. This some people call as the fundamental theorem of calculus. Fundamental theorem of calculus. And as you can see, it's got a very important sounding name. And important things tend to be sometimes hard to prove. Not always, but sometimes they tend hard to be proved. So we are not going to prove it over here. I'm just going to give you the statement, and I will write it for it. The fundamental theorem of calculus just does not apply to ideal gases, it applies to any function. So let's write it down over here. What it says is that limit of a sum, or limit as a sum of a function going from n is equal to 1 to n, f of x delta x, this limit as capital N tends to infinity can be replaced by the value of x1 over here and the value of xn over here, f of x dx, where in order to calculate this, all we need to go do is to calculate that function d of that function g of x, differentiating which would have given us the f of x. So the operation of calculating the area under the curve by chopping it into very, very small parts has been split into something which at first glance seems completely unconnected, that go and figure out the function differentiating which would have given us this function that we are trying to integrate. So this is a beautiful relation, and this is why we were able to calculate the work done by a gas by using this formula. Here we used a generic property. So here, this is an example of a definite integral. And where we use integral x1, x2, f of x dx. If you could figure out what is the g of x, then this would be g of x2 minus g of x1. We also will see lots of indefinite integrals, where you won't have these limits. You will leave the limit up to the user who wants to work with this. And then in this case, it will be g of x plus some constant c. And we will be seeing examples of both. So in the next module, we will use this to calculate the area under curves. And what we will do is to start by thinking of functions g of x whose derivative is well known, that we have calculated the last time in the last module, such as e to the power x. We know the derivative e to the power x. Cosine of x, we know the derivative is minus sine of x. X squared, we know the derivative is 2x. So we will work in this opposite way and use the functions, use our knowledge of functions whose derivative we know to calculate area under curves. Then I will give you a list of common integrals. There are ways of calculating it. Mostly the best way is to figure out what is it that differentiated would have given you this integral. But then what happens is that once you have a list of such basic integrals, you can actually go and manipulate complicated integrals by expressing them as a function of these basic integrals. And you don't always have to just go and sit and kind of meditate as to which function when differentiated would have given you this integral. So this will be the topic of next module. With that, thank you very much.